Greetings, ladies and gentlemen, future Martians, potential Jupiter vacationers, and the curious Earth-bound soul in search of cosmic knowledge. Welcome back. Today, we're going to explore a fascinating subject that could reshape how we travel through space: plasma propulsion. For decades, we've relied on chemical rockets, those towering vehicles powered by engines that spew flames and generate massive thrust. They've brought us to the moon, launched satellites, and enabled human space stations. But as we dream bigger, thinking about Mars, the outer planets, and perhaps beyond, we face a critical question. Is there a better way to travel through the solar system than traditional chemical rockets? Plasma propulsion might be the answer. Often grouped under electric propulsion, plasma thrusters operate on a completely different principle than the usual chemical rockets that ignite propellant in an explosive reaction. In plasma-based engines, we rely on electricity, either from solar panels or possibly from nuclear reactors in the future, to ionize a propellant and accelerate those ions to extremely high speeds. This leads to engines that are more fuel efficient than anything we've used before. But before we begin, let's establish what makes plasma propulsion so special. In chemical rockets, you rely on rapid combustion to provide a short but powerful burst of thrust. By contrast, plasma thrusters usually provide a gentle push, a much smaller force at any given moment. But they can run for a very long time. Over days, weeks, or even months, that gentle push adds up, ultimately reaching speeds much higher than you can achieve with short chemical rocket burns, unless you haul enormous amounts of propellant. This idea isn't new. Scientists began experimenting with electric and plasma propulsion decades ago. Today, space agencies and private companies use these thrusters for satellite station keeping, orbital maneuvers, and even deep space probes. As technology advances, we might see plasma propulsion play a key role in human missions to Mars, and possibly in building infrastructure around the moon and other planetary bodies. By the end of this video, you'll have a solid grasp of plasma propulsion, what it is, how it works, where it's used today, and what it could become. So, get comfortable, and let's start by revisiting the basics of rocket propulsion. Understanding how we got here will shed light on why plasma propulsion is such a big leap forward. To understand plasma propulsion, it's important to first grasp what we mean by rocket propulsion in general. All rockets, whether chemical or electric, follow the Tsiolkovsky rocket equation. Don't worry, I won't bore you with a physics lecture. The Tsiolkovsky rocket equation is a simple way to explain how rockets work. It tells us how fast a rocket can go based on two key things: how fast the rocket pushes out its fuel and how much of the rocket's weight is fuel compared to everything else. This is important because it helps us understand why rockets need so much fuel. For example, to escape Earth's gravity, a rocket needs to reach extremely high speeds. Since traditional rockets can only push out fuel at certain speeds, they have to carry a huge amount of fuel to achieve those speeds. That's why rockets are so big. Most of their size is just fuel. So it becomes very challenging when we think of doing more complex missions like going to Mars or Jupiter or maybe Saturn. You often need multiple stages and a lot of propellant. Each additional stage or maneuver also triggers a mass penalty, meaning you need more fuel to carry the fuel, which leads to exponential growth in rocket size. That is why we needed a different solution. Traditional rockets are great for launch and rapid velocity changes. But for longer journeys in space, we need something more efficient. That is why scientists invented electric propulsion. This is a propulsion system that uses electricity to accelerate particles and generate thrust. Electric propulsion, which includes plasma thrusters, can achieve exhaust velocities far exceeding chemical rockets. Some ion thrusters have exhaust velocities of 15, 20, or even 30 kilometers per second, drastically reducing the propellant needed to achieve a given delta V. The only trade-off is that electric and plasma systems typically provide low thrust, so it takes longer to accelerate to high speed. That's perfectly fine for many satellites and deep space probes, which can afford to spiral outward over months. Traditional rockets are great for launch and rapid velocity changes, But for longer journeys in space, we need something more efficient. Before we dig deep into this fascinating technology, let's talk a little about what a plasma is. When we talk about states of matter, most of us think about solid, liquid, and gas. But there's also a fourth state, plasma. Plasma is essentially an ionized gas, meaning that some or all of its atoms have lost electrons, creating a mix of free electrons and positively charged ions. If you are wondering where we can see the existence of plasma, the first thing that comes to mind is our sun and other stars. They're giant balls of plasma held together by gravity. Also, a flash of plasma is created when the electric potential in storm clouds breaks down the air's resistance. Coming closer to the reach of your hand, the neon lights, the glow in a neon sign, comes from ionized gas inside the tube, which is pretty close to plasma. Now, I think you got the main point. Why do we need plasma for electric propulsion? Yes, because it's made of charged particles, and plasma can be manipulated using electric and magnetic fields. By controlling these fields, we can accelerate ions to high speeds, creating thrust for a spacecraft. Think of a hairdryer analogy. You blow hot air out to move objects like pushing a small piece of paper. Now imagine if you could charge that air and accelerate it using a strong electromagnetic field. You'd end up with a stream of particles moving much faster than you could achieve through mere heating. That's the basic principle behind many electric thrusters. Okay, now let's talk about the plasma thrusters. Plasma engines use different methods to ionize their propellant. Some use electron bombardment, others use radio frequency waves, and some rely on electric arcs. Once the gas is ionized, electromagnetic fields guide and speed up the ions, propelling them out the back of the engine to generate forward thrust. The biggest advantage is the potential for high exhaust velocity. If your ions exit at tens of kilometers per second, you gain a lot more delta V per unit of propellant. That's exactly what we want for deep space travel. The main limitation is that the thrust is small. But if time isn't critical, that small thrust can be applied consistently, accelerating the spacecraft to very high speeds over long durations. Now that we understand what plasma is and why we need it for our electric propulsion technology, let's discuss the basics of electric and plasma propulsion. Electric propulsion is an umbrella term that refers to propulsion methods that use electricity to accelerate a propellant. Plasma propulsion is a subset of electric propulsion where the propellant is ionized into plasma before being accelerated. This includes ion thrusters, Hall effect thrusters, magnetoplasma dynamic thrusters, and more. So how does it work? We can divide this into three parts: ionization, acceleration, and power source. Ionization is when a neutral gas, often xenon, argon, or krypton, is injected into the thruster chamber. An electric process strips electrons from the gas atoms, creating positive ions and free electrons, forming plasma. Acceleration is achieved using either electric fields, magnetic fields, or both. These ions are forced out of the engine at high velocity. Electrons are also often released to neutralize the ion beam, so the spacecraft itself doesn't become overly charged. So where does the electricity come from? The electricity typically comes from solar panels, or in some future concepts, from a small nuclear reactor. Now that we have the overall picture, let's dig deeper into the different types of plasma thrusters you might hear about, from the well-established Hall thrusters to more experimental concepts like VASIMR. Each has its own strengths and weaknesses, but all promise a future where spacecraft can move around the solar system more freely than ever. Within plasma propulsion, there's quite a variety. Let's look at some of the main categories. First up, ion thrusters. This is often what people imagine when they think of electric propulsion. These use a grid mechanism to accelerate ions. Normally, xenon gas is ionized, and the positively charged ions are drawn toward a negatively charged grid, exiting at high velocity. The impulse of this can be very high, often above 3,000 seconds, meaning extremely efficient use of propellant. But remember, the thrust we get from this is typically low, measured in millinewtons to a fraction of a newton. NASA's N-STAR engine on the Deep Space One mission used ion thrusters on the Dawn spacecraft. The second type is Hall effect thrusters. These use a combination of electric and magnetic fields. Electrons are trapped in a magnetic field and swirl around, ionizing the incoming gas. The resulting ions are accelerated by an electric field out the back. These thrusters are simpler in design with higher thrust density than many gridded ion thrusters. We commonly use these for station keeping in geostationary satellites and some deep space probes. The third type is called magnetoplasma dynamic thrusters, or MPD. These use a strong electric current that arcs through the propellant and magnetic fields to help accelerate the ionized gas. These thrusters can produce higher thrust levels if enough power is available. Yes, that's the main drawback of these thrusters. It requires massive power. And the fourth type is still a concept in progress. This is called the Variable Specific Impulse Magnetoplasma Rocket, or VASIMR. These thrusters will use radio waves to ionize and heat the propellant, then magnetic fields to direct the plasma out the nozzle. Ideally, these should be able to switch between higher thrust or higher efficiency depending on mission needs. That's why this research is so important. Once we achieve this, we can use the same thrusters at different parts of a longer mission, depending on the need for higher thrust versus higher efficiency. Each thruster type fits different mission profiles. A small satellite might only need a modest Hall thruster for station keeping. A deep space science probe might require an ion thruster with an extremely high specific impulse for a multi-year mission. Future crewed spacecraft might look to advanced concepts like MPD or VASIMR if they can get the necessary power. Let's see where these thrusters have already been used in real missions. This will help illustrate their strengths and show that plasma propulsion is not just theory, it's already out there in space. Plasma propulsion has already proven its worth. It was used by NASA in 1998 in the Deep Space One mission with an ion thruster called N-STAR. It conducted a flyby of asteroid 9969 Braille and comet Borrelly, demonstrating that ion propulsion could be a viable primary propulsion method for interplanetary travel. In 2003, ESA used a Hall effect thruster in ESA's Smart 1 mission, which orbited the Moon using only about 60 liters of xenon, proving how fuel-efficient these engines can be. This mission showcased how a spacecraft could spiral slowly away from Earth and enter lunar orbit with minimal propellant. In 2007, NASA used 3 xenon ion thrusters in NASA's Dawn mission. Dawn's ion propulsion allowed it to leave orbit around one asteroid and rendezvous with another, a feat that would have been extremely difficult or impossible with conventional chemical rockets due to fuel constraints. Apart from these, most new geostationary satellites and many low Earth orbit constellations use electric propulsion for station keeping and orbit raising. These reduce launch mass, save on propellant, extend satellite lifespans, or increase payload capacity. These examples show that plasma propulsion isn't a far-off fantasy. It's already a trusted technology in various sectors, government and commercial. As power systems improve, the applications for plasma propulsion will only grow. One of the most exciting frontiers is human spaceflight, which we'll discuss next. The idea of sending humans to other planets, especially Mars, has been around for decades. Chemical rockets can theoretically transport astronauts to Mars in about 6 to 9 months, depending on orbital positions. However, that's a long time for astronauts to be exposed to cosmic radiation and microgravity. Furthermore, carrying enough fuel for the round trip plus safety margins is a massive challenge. So how could plasma propulsion help? Plasma thrusters use less propellant to achieve large velocity changes. Although the thrust is small, a constant push can, over time, achieve higher speeds. Think of it this way: you use a normal thruster to launch into low Earth orbit. Then you start the ion thrusters. Initially, you will stay closer to Earth for a few days, but slowly, as it starts gaining speed, you can complete a 9-month journey to Mars in maybe 3 months. That's huge. Some advanced designs like VASIMR, if powered by nuclear reactors, could potentially bring the travel time to Mars down to a few tens of days or a couple of months, depending on how much power is available. Faster trips mean astronauts spend less time in deep space facing harmful radiation. With more efficient propulsion, you could deliver heavier payloads, habitats, supplies, and scientific equipment. Electric propulsion can allow more frequent corrections or changes in trajectory, making fine adjustments on longer journeys much more efficient. And surprises space throws at us on our journey, we can dodge them easily. Then why are we not using it already to go to Mars? Well, there are still some barriers we need to overcome before we can pack our bags for Mars. We need a megawatt-class power source for high-thrust plasma propulsion if we want faster trips. Solar power diminishes as we move away from the sun. Nuclear reactors in space could provide constant large-scale power. Designing a crewed vehicle that integrates living quarters, life support, radiation shielding, and a powerful electric propulsion system is complex, and above all, before we put a human in front of these engines, we need to make it extremely reliable. That takes years of ground and in-space testing. Plasma propulsion won't replace chemical rockets for lifting off from Earth anytime soon. But once in orbit, these advanced engines could transform how we move people and cargo around the solar system. It might start with cargo ships using electric thrusters to pre-position supplies on Mars, followed by faster human-rated electric ships once the technology matures. Advanced propulsion systems come with advanced problems. Large solar arrays can work near Earth or the inner solar system, but they become less effective around Mars and are nearly unusable in the outer solar system without massive surface area. A small nuclear reactor could provide steady electricity, but launching nuclear material faces strict regulations and poses safety and public relations challenges. Time is also a challenge. Yes, we say these can reduce travel time, but plasma thrusters produce low thrust. They can't do quick maneuvers like orbital insertions around large planets unless they plan carefully over long periods. High-power thrusters also generate more heat that must be radiated away in the vacuum of space. Large radiators add mass and complexity. Over time, high-velocity ions can erode thruster walls. This shortens the thruster's lifespan if not carefully managed. That's why researchers are looking for better ceramics and metals to withstand long durations of ion bombardment. Also, it's not only about the research, manufacturing, and testing. Developing high-powered electric propulsion and nuclear technologies can be expensive, requiring specialized facilities for testing. We need thrusters that can operate at hundreds of kilowatts to megawatts for crewed flights. That's a big leap from the current 5 to 20 kilowatt thrusters used by satellites. Many of these challenges have solutions under active investigation. For instance, NASA and other agencies are working on advanced solar arrays with much higher power density, and companies around the world are developing safer, more compact nuclear reactors. Material science is also seeing breakthroughs in ceramics and tungsten alloys that can handle harsher environments. In short, plasma propulsion is promising but needs further refinement. Let's now shift to what the future might look like if these hurdles are overcome. How might it change not just exploration, but even commerce and resource utilization in space? Imagine a future where regular supply runs to the Moon and Mars are as routine as cargo flights on Earth. Advanced electric cargo ships powered by solar panels for nearby destinations or nuclear reactors for longer journeys gently spiral through space over months, carrying habitats, rovers, and resources to establish permanent outposts. Mining equipment might venture to near-Earth asteroids, extracting valuable metals and water, the latter split into hydrogen and oxygen to fuel deeper space missions or sustain orbital stations. With plasma propulsion, even the outer planets could become accessible. Spacecraft could explore Jupiter's icy moons or Saturn's Titan in a single mission, changing orbits efficiently. Human exploration could take a giant leap forward with faster, continuous thrust propulsion, reducing travel time to Mars and minimizing radiation exposure. Yet all these visions depend on overcoming the power challenge. Without advanced energy solutions like megawatt-level nuclear reactors or space-based solar arrays, these missions may remain conceptual. If achieved, this new era of space exploration could transform industries, spark innovations, and inspire a new generation to push the boundaries of science and technology, driven by a global commitment to explore and utilize the vast resources of space. Plasma propulsion is more than just technology. It's a vision for the future of space exploration. By enabling efficient long-duration thrust, It opens the door to interplanetary missions, asteroid mining, and sustained human presence on Mars and beyond. While challenges like developing powerful energy sources remain, the progress so far from missions like Dawn and Smart 1 shows that we're on the right track. Space exploration has always been about transforming dreams into reality. Plasma propulsion is quietly revolutionizing how we move through space, paving the way for humanity to become a truly spacefaring civilization. Let this be a reminder to keep looking upward, to the stars and the infinite possibilities they hold.